Alright, so the last video ended with this statement, which is also known as the Heine-Borel theorem. And we have actually already seen this, but let's again see what it says. X is a subset of R. Then for this subset X, the following two statements are logically equivalent. That means if one of them is true, then the other also must be true. And the statements are this: X is both closed and bounded as a subset of R. And the second statement is that given any sequence AN whose members are coming from X, in other words, the sequence is taking its values in X. For any such sequence, there is a subsequence of the original sequence that is convergent, and it converges to some point L in X itself. Okay, so now we have to prove that these two are equivalent. So let's start the proof. So we will first prove that statement A implies statement B. So assume A. That means we are assuming that X is closed and bounded. So let us now consider such a sequence, and we have to prove that there is one such subsequence. Let AN be a sequence in X, and I have already said this before, but again I am saying that whenever I write a sequence in X, by that I mean that all the terms of the sequence are elements of X. Okay, then what do we get? Now we will first use the hypothesis that X is bounded. Since X is bounded, X will be a subset of a closed interval of this form, because that's what boundedness is by definition, for some positive real number n. Now all the terms of this sequence are elements of X, so automatically all of them are elements of this closed interval as well. Thus AN is a sequence in this closed interval, i.e. We can also say the same thing like this: the absolute value of AN is less than or equal to n for all indices n, for all natural numbers n. But then AN by definition becomes a bounded sequence, and we already know from Bolzano-Weierstrass theorem that every bounded sequence has a convergent subsequence, and that theorem is the theorem 668. So by theorem 668, there is a subsequence ANJ that converges to some real number, okay, some L. But actually we are not done yet, because we want that L to in fact lie in X, and this is where closedness of X comes into play. Okay, X is bounded, fine. So from boundedness we get this much, but after that if you use closedness of X as well, then this L will belong to X. But why though? That's because you see, you are getting a sequence, a subsequence of the original sequence. Now the original sequence had all its elements in X, so automatically the subsequence also has all of its elements coming from X. So that means this is a sequence of elements in X, and now that sequence converges to a real number L. So by a previous result, L becomes an adherent point of X. But X is closed, so it must contain all of its adherent points, and that's how L will have to be inside X. And we will of course refer to the actual result, since X is closed. So closedness will now force this L to be in X. And that result is corollary 9,170. Is it not? Yes, it is. Since X is closed, it follows from corollary 9,117 that L belongs to X. In fact, this corollary is that result which gives us a sequential formulation of adherent points, that is characterizing adherent points using sequences. So that proves that A implies B. Conversely, assume B. And assuming B now means what? It means that whenever you consider a sequence whose elements are all coming from X, in other words, in our language, a sequence in X, any such sequence, then such a sequence must have a convergent subsequence with limit again in X. Okay, so that is our hypothesis now. We now have to prove that the set X is bounded and closed. Let us first show the boundedness, and in fact let us first suppose that it's not bounded in order to get some kind of contradiction. Suppose X is not bounded, then X has okay, I should use the word either. Then X either has no upper bound, or it has no lower bound, or actually both also. That possibility is also there. It may be the case that X neither has an upper bound nor it has a lower bound. And we are now going to handle the case where X does not have an upper bound. And the case where it does not have a lower bound but may have an upper bound will be left to you. Okay, so you will try to handle that case. Suppose x has no upper bound, then the following sets are all going to be non-empty. Then the intersection of x and this open interval, half infinite open interval, is non-empty for all natural numbers n. But why? That's because for any natural number n, in particular n is not an upper bound of x. So that means there will be at least one element in x that is greater than n. But that element will of course also be in this interval. So that element would belong to the intersection. So all such intersections are non-empty. Okay, so now we are looking at a collection of non-empty sets. So this is a perfect place for us to use the axiom of choice. Now, by the axiom of choice, there exists a sequence. A sequence, actually a tuple, but what is the index set that is indexing this collection? The set of natural numbers, so that's why a sequence. A sequence yn of real numbers such that, so we are choosing yn from the nth set. If this denotes the nth set where n starts from 0, then yn is coming from this intersection. For all n belonging to the set of natural numbers. So because of these things, these relations, you can clearly see that each yn is in x. So that means this is a sequence in x. And what we have assumed is that for any such sequence, there is a subsequence that converges to some element again in x. That is our hypothesis. That is the assumption B. Now, by the hypothesis, there is a subsequence Ynj of the original sequence, of course. You can see that converges to some element of x. It converges to some element of x, but really the fact that it converges is what will work for us. I mean, we only need that much. Let's see why. Okay, now just like all the yns are coming from these intersections. So correspondingly, these YNJs will also come from the appropriate intersections, because the terms in this sequence are after all also in this sequence. That's why it's a subsequence. And now this is the thing. Now the sequence Nj, the sequence of the suffix values Nj, is strictly increasing. Why? Because this Nj's, this sequence is itself a subsequence of the sequence of all natural numbers. So that's why it is naturally strictly increasing. Strictly increasing in the sense that Nj is strictly less than Nj plus 1 in that sense. And Ynj. Now Ynj will belong to this intersection where in place of n we have Nj. So that's why Ynj has to be greater than Nj, strictly greater than Nj, because we have an open interval here for all natural numbers j. So if the Ynj's are greater than Nj and the Nj's themselves form a strictly increasing function, then do you think these Ynj's can be a bounded sequence? Of course not, because these Nj's are natural numbers and the Ynj's are greater than even them. Okay, but then this sequence is unbounded from above, but after all unbounded. However, this is a problem. This is a problem because this sequence is convergent and as a result it's bounded. We already know that every convergent sequence is bounded, but at the same time we are getting the conclusion that this is unbounded. So this is a contradiction. And it is a contradiction to this, in fact, that result which says that convergent sequences are bounded, and that is corollary 6.1.17. But this contradicts corollary 6.1.17. So that means something must have gone wrong. And the only thing that went wrong is our supposition that the original set X is unbounded. So our supposition is wrong. i.e. X must be bounded. So that's how boundedness of X is established. But again, keep in mind that it's not complete. This itself would not imply that X is bounded or our supposition is wrong. You have to also show that when X is not bounded from below, a similar contradiction arises. Once you do that, then only you can say that X is bounded, okay, because of that contradiction. But anyway, that is left to you. So we have shown that X is bounded. Now we will show that X is closed, and in doing so, we will take the help of sequences again. Let Okay, closedness means what? Closedness means we have to show that X equals its closure. But we already know that closed or not, this containment is always true. So equality demands that we show this. In other words, we show that every adherent point of X is actually inside X itself. And that itself can be expressed in terms of sequences, because when we say that there is an adherent point of X, then automatically by that result there is a sequence in X that converges to that point. So let us start with a sequence in X itself. Let Zn be a sequence in X converging to some real number Z. But our assumption, that is statement B, says what? That such a sequence will have a convergent subsequence that converges to something inside X itself. By hypothesis there exists a subsequence Zn J such that the limit of this subsequence, there exists a subsequence, I am not explicitly writing this, but a convergent subsequence, okay, which becomes clear from this statement itself, that the limit must belong to X. But the original sequence itself is convergent. And so, from properties of convergent sequences and their subsequences, this limit of the original sequence actually should also be equal to the limit of the subsequence, and that will force Z to be inside X. And the result that says so is the corollary 9117. No, okay, corollary 9117 comes afterwards, but what is this one? Oh, we are not referring to the actual result, okay. You understand what result I am talking about. The result that says that any subsequence of a convergent sequence is itself convergent and converges to that same limit as the original sequence, that result. But then the more you use these results, the less you refer to them actually, that is using the theorem number or those things, because the more you use them, the more natural they become. So at some point you just give up mentioning anything at all. They become so natural and obvious. But then this limit is actually equal to this limit which belongs to X. So that's how this Z belongs to X. Hence, by this corollary 9117, X is closed. So we have ended up showing that X is both bounded and closed, and this completes the proof. And this completes this section also. In the next analysis update, we will start solving the exercise problems. Some of the problems are in fact proofs of these results that we have gone through, because we have proved many of them. In fact, I think all of them we have proved here itself. So those things are already done for us, but there are other exercises also. So we will do that next Sunday. And this coming Tuesday, where we have another upload, we will do what? Number theory. Okay, so if we are actually solving problems right now, exercise problems, then the solutions will appear as community posts and not as a video. Okay, so see you on Tuesday with those things. Until then, this is me, Lucifer from A Mathematical Room. Have a nice night.